Hi everyone, my name is Anca Dragan, and I wanted to talk to you today about our latest thinking in how to get robots and also AI systems more broadly to assist people, to help us out. So what do I mean by assist people? What is assistance? Well, let me share a few examples with you of recent tasks that we've been working on so that you get an idea of what I mean. So one of the tasks is assistance with navigation. Here, imagine you're visually impaired and you are trying to navigate in a house. And you can't directly perceive the scene in front of you. Looking kind of at the scene from a top-down view, you're trying to go somewhere, let's say here, but you don't know exactly where you are. Here, you could be there, and you don't know exactly how to get to where you're going. And so you need a little bit of assistance, of guidance. So the question is, how can a guide, an AI-powered assistant, sort of give you hints and help you get where you want to go? Another example is for users with severe motor impairments who are, say, trying to type a sentence in their email. So you can see a sentence at the top there. And what we did is we set up an eye gaze-based interface that presents a set of words to the users like so, and it waits for the user to look at the desired word and then takes a picture of the users through their webcam. And given this webcam image, the interface then tries to predict which word the user wants to type. So it assists in the sense of helping the user actually type out what they want. And we're also looking at this same setup, but in collaboration with UCSF, the Department of Neurology there. They have a patient with quadriplegia. They implanted an ECOG array into his motor cortex. And so for him, instead of gaze, we're using the brain signals, what we're recording from the ECOG array. And we want to map that to the word that he wants to type. And the final example is one where you're trying to operate a robot with complex dynamics. Our stand-in for that here is the Lunar Lander from the Lunar Lander Atari game. And it's really hard to pilot this craft, even though it's in simulation. So these are users without any motor impairments, trying hard to land this in between the flags and not crash. And they're doing a pretty poor job, as you can see. I also do a really bad job when I play this game. So these are examples of assistance. And in all of these tasks, users have a policy mapping their state that they're in to sort of the input that they provide to an interface. And then a decoder can take that input and translate it to actions that the system can execute, right? Be it which word you're typing or the controls for the Lunar Lander. So their input would be kind of keyboard input, and then these would get translated by the decoder to controls for the lander. And a typical way to do assistance here is to look at the user's actions, which are going to be really noisy and suboptimal. And instead of just playing them out, executing them on the robot, the assistant would actually try to infer what the user's intent is, what their goal is. For instance, where are they trying to land? Or where in the house are they trying to go? What sentence are they trying to type? So that's their high-level goal. And then the assistant, based on this goal or on a distribution, would take actions on the user's behalf to better achieve that goal. And this presents some challenges. So we've gotten pretty far with this kind of methodology for assistance. I've worked on this. A lot of other people have worked on this, but we're kind of getting stuck on some things. So one challenge is that same suboptimality in the user actions that requires you to have assistance to begin with, that suboptimality also makes it really hard to figure out what the user's goal is. Like in the Lunar Lander, they overshoot the goal to the left or to the right, and that leads to wrong inference. You can see here a distribution over goals for these two examples. And by overshooting sort of to the right, that makes the assistant infer the goals on the right as opposed to the true goal, which is here in green. And then the assistant assists with the wrong goal, which is bad. Now, even if we inferred the correct goal, we're then kind of doing the task for the user. So we're taking away the person's autonomy by just completing the task for them and overriding their input. And that's not a very empowering experience. So here in this example, at some point, the assistant just takes over, not here. about here. They just take over and just land. And sure, that gets the task done, but it deprives the user of their autonomy. And so we've been wondering, could we do assistance differently? Could we, instead of correcting the user's actions to make them optimal for their goal, could we somehow just let the person do their thing because they know what they want and enable them to take the better actions, the close to optimal actions by themselves? Could we assist them such that the actions that they're actually commanding end up being the right actions to take? And I think that would be kind of the holy grail. You're not intervening and overriding at the end. So you instead of just correcting their actions at the end, you're somehow making it, injecting assistance in some way so that these actions that come out from what the user is commanding are just the right ones to begin with. And so to figure out how to begin thinking about this challenge, we had to ask ourselves, well, why are users taking actions that are suboptimal? Why do they need assistance in the first place? Why are these actions that are coming out so noisy and bad? And there's many answers to this, but one answer that we've been investigating is that part of what explains why the actions are suboptimal is that this picture of the person sees the state and that's what they use to decide on what to do is wrong. Much like robots, people don't get to see the state, they get to see observations, right? It gets sensory input. And they're acting not based on the state, but based on their belief about the state of the world, their estimate of the state. And that estimate could be wrong. If that estimate is wrong, that leads them to make wrong decisions. So it leads to suboptimal actions when you look at the correct state that they're in. Now, why on earth would their belief be wrong? Well, plenty of reasons. Here's some examples. It might be wrong because of information overload. So people might not be able to pay attention to many different sensors at the same time, which means that they're not going to have the proper estimate. Even see lens distortions that are causing users to overestimate distances to objects. And in general, we know that our perception system is messed up and wrong in some ways, because otherwise optical illusions wouldn't be a thing, right? So all humans misestimate the state here, and that's because of these biases and shortcuts that are in our perception system that are really helpful in some ways and really damaging in others. So if we want them to take better, closer to optimal actions, if we want them to command better actions, then our idea is that instead of correcting their actions, we should see if we can correct their belief, as that in turn enables them to make better decisions and therefore to take better actions. Now, we can't just incept the belief into the user's head, but what we can alter in a lot of tasks, in a lot of cases, is the observations that they receive. So the key idea in this work was that the full observations are not necessarily the most informative about the state of the world, especially when they're processed incorrectly by the user due to the systematic biases in their perception. So our thought was, let's look for other observations, sort of kind of lie to the user about what they're seeing. Other observations, instead of OT, some OT tilde, that when the person processes that through their sort of biased processing perception system, they end up nonetheless with a better belief, with a more correct belief. So the way we operationalize this is by using an automated assistant to process the full observation on behalf of the user. This assistant performs state estimation unencumbered by systematic biases or perception difficulties that the user has. And then the assistant provides the user with a modified observation, this OT tilde, that when processed by the user suboptimally, incorrectly, it leads to them having a more accurate belief than they would if they just saw the raw, unfiltered observations, OT. And so the way we come up with OT tilde formally is we try to minimize the KL divergence between the assistant's beliefs and the user's beliefs. After the assistant processes the true observations, right, you end up with a belief. It synthesizes a modified observation that it thinks will make the user believe in the same state as the assistant. So that will induce a similar belief in the user when the user processes it with their model BH hat here, that the assistant has when the assistant processes the correct observation OT with the correct model B. Now, why is the assistant belief the target here? Why is that the holy grail? Well, because robots don't suffer from information overload. They can apply Bayes' rule correctly. And so, of course, they don't know exactly the state, but they have the correct belief about the state given all the observations that they received. And so we're trying to minimize the kill divergence between what the user ends up with and what the robot ends up with. The challenge, what's hard about this, is that we don't have access to the user's internal estimation process. We don't have access to this BH hat. So what we propose is to learn it from demonstrations of users' actions. So we look at user actions and then we try to kind of back derive what a BH hat is that fits that. And so we model the likelihood of the user taking a particular action AT, given a history of observations and actions so far, by marginalizing out the state, right? So you see this integral over S, and what that does is it helps us break down this likelihood of the user action into two components. First, there's a near optimal policy for the completed task, so AT given ST. And then there's a parametric representation of the user's sort of belief estimation process. So that BH hat, which we can parameterize however we want, for instance, with a neural network. And what's nice is that we can compute the near optimal policy. We can observe these actions on the left-hand side. And so we can use this equation to back derive what the belief model for the user is that's consistent with the data that we're seeing. The way we train this is by optimizing the user's estimation model so that those data parameters in the belief model to maximize the likelihood of the user actions that we observe, the actions that the user end up taking. So that's what we do. And we applied this to assisting people navigate indoors. So again, they can't directly perceive the scene in front of them. They're somewhere over here. They're trying to reach a position over there. If they think they're in one corner, but they're actually in a different corner, that's where they're taking suboptimal actions. So let's try to fix that. So we have an agent guide that can see the user's egocentric scene and figure out what objects are around for them. And the guidance that this guide, we have some options here of how the guide can intervene. The assistant that they provide is to tell the user about what is around them. You could also have vests that are haptic and so on. But we went with tell the person what's around them. And a default guide would just tell you about the stuff that's around, sort of in an unfiltered way. That'd be a bit overloading in terms of information and not necessarily very informative. But nonetheless, you'd update your understanding of where you are based on that to the best of your abilities, and you try to navigate. Now, in contrast, our guide selects objects to tell you that are going to be informative to you. And this tends to result in more accurate user beliefs, and as a result, in the user taking less time to reach their goal. This is what we see in our experiments. We also looked at a different task, this Lunar Lander task, and we made it a bit more complicated, where we made it difficult to see where the lander is, and we added this horizontal tilt bar as an indicator to help user perceive the angle of the lander. And what our assistant learns here to do is pretty cool. It learns to exaggerate this tilt of the lander to kind of compensate for what seems to be an apparent inability that we have to correctly estimate the tilt ourselves. So on the right, you see what is actually happening. And on the left is what you would see by default. And then in the middle is and I'll play this again. In the middle, you see what the assistants decide to show you. And it's wrong. It's not the correct tilt. Essentially, by the agent lying to you about how tilted the lander is, you're able to keep the lander more level. And we see this in a user study. And so basically what seems to be happening is that if you have a slight tilt, it's not noticeable and people don't end up correcting for it and then they crash. However, if you see this exaggerated tilt, you have an easy way to detect it, and it turns out you don't overcorrect. You correct just right so that you end up keeping the thing level. And that angle is different for every different user. So there's some customization. It seems like each of us can benefit from a different level of exaggeration, and the assistant picks up on that. Okay, so in a nutshell, we've been getting creative with how to enable users to take good actions on their own, which I think is a pretty empowering way to assist, right? Instead of just doing stuff for them, just get them the information that they need in order to make the correct decisions by themselves. And in the remainder of our time together, what I wanted to share is 2 quick alternative ways through which we can do this, to which we can improve these actions that people are taking besides correcting their beliefs. So if we want their actions to be good, to be close to optimal, another avenue besides correcting beliefs, and this is perhaps a much more obvious avenue, is to just improve this decoder that maps between their interface, their input, like a keyboard or gaze, to the actions that apply to the sort of the system. And how does this decoder work, and how could we make it better? Well, let's remember this typing task, for instance. The overall goal here is a sentence at the top. The actions are the words. These are the decoded actions, but the input is gaze. So how do you train a decoder from gaze or brain signals to the commanded word? How do you do that in the first place? And so what is there to improve on? Well, it turns out there's something to improve, because the standard way in training these decoders, sort of having this calibration stage of the interface through supervised learning. So it requires, we see it here happening, a new user to provide this paired data of inputs and actions, and then you do supervised learning to train that. And this can be time consuming and disruptive. And actually, what is even worse is it drifts over time. Our patient at UCSF, for instance, we see the readings at the beginning of the session. They're very different from the readings that we get for the same sort of task at the end of the session. So you see drift happen, and you see this interface, the decoder, degrading in performance, even over the course of a day or even a few hours. And so there's drift, which means that these interfaces have a lot to be improved on. And here's what happens when you use them. So you start typing, and the decoder inevitably messes something up. And when that happens, you usually have some sort of backspace or undo action. You have to, otherwise you won't be able to fix anything. So this could be, for instance, sort of their sip and puff interface. And our simple observation here is that there's a lot of information in that backspace that we should be using. So instead of learning a decoder once and keeping it fixed, we should notice that whenever the user does Backspace Run, does something, they're leaking information. They're telling us information about what the decoder should or really shouldn't be doing. And we can learn from that. And so that's what we did. Our method for learning from these backspaces is pretty simple. We present a set of words to the user. We take a picture of the user's eyes through their webcam, then feed this input to our selection policy. We sample an action from this policy. The user sees this action, compares it to their desired action, and then they decide whether or not to backspace. And this decision to backspace kind of naturally provides our system with feedback that it can use to derive a reward signal. And then train a policy through reinforcement. So in particular, we train a reward model, we train a reward signal to be kind of this binary classifier that predicts the likelihood of this backspace to happen. And what this lets us do is it lets us actually use the default interface and the default decoder and improve upon it. So the way we use this trained reward model is as an update, a likelihood update on the default interface. So, right, so we take the default interface, we update it with the reward model, and then that's, lo and behold, our interface. And what's cool is that it doesn't make any assumptions about the type of user input. So in addition to conducting experiments with users who provided gaze input, we also tried this with our patient at UCSF who used their ECOG brain-computer interface to provide input to the system. And I have to say that this was by far the most exciting part of this project, even though we had to really simplify things for this to work with the patient. So we just had 4 words, as you can see here in the top left. Nevertheless, it was so cool to see a person thinking stuff and then being able to type. And we saw that just sticking with the default calibrated decoder, so shown here in the gray bar, ends up with significantly lower accuracy when compared to this way of learning online. So it seems to actually be working for them. And interestingly, we saw that the default interface, maybe because of this drift issue that I was talking about, it ends up never predicting the topmost button as an action, so the topmost word. So there's a 0% recall rate for that action. And in contrast, we saw that with online learning, when you do this reinforcement learning thing on top, you achieve 70% recall on the topmost action. And that's cool, and it's important because it suggests that the online learning can overcome these challenges in the default interface over time as you're getting these corrections. I'm not going to get into details on that, but we see with gaze input, here we actually ran a user study with 12 participants, and we found that learning a reward model substantially improved performance here as well compared to the non-adaptive interface. And maybe what was more interesting is that the default interface performed particularly poorly for the users where the online training helped the most. So sort of that makes sense. So what we see is that by learning the decoder online and sort of back to the beginning of the talk by correcting the user's beliefs, these are both ways through which we can really empower users to take the right actions for themselves. And they can be good alternatives to sort of having the system try to figure out their long-term goal and override their actions. And now to wrap up, I just want to give you one final idea for how to achieve this type of assistance. And we got the inspiration again from Lunar Lander. We got a lot of mileage out of this Lunar Lander game. So if we look at what's happening here, the lander becomes so unstable that it's really hard for the user to do anything. No matter what their goal is, no matter what they want to land or what they want to do with the aircraft, maybe just they want to hover it or something like that, they can't do that because they so easily go to these states of instability from which they can't do anything. And we thought that's the problem. We thought that maybe we don't really need to actually infer their goal to help them. What we need to do is get the system to be more controllable so that they can help themselves. So we've thought about this as increasing the user's controllability over their environment. That is the ability to affect actions, to affect the environment through the actions that they're taking. And mathematically, we formalize this notion via this information theoretic concept of empowerment, the mutual information between the user's actions and the resulting states. So low empowerment situations are those in which you're kind of stuck and you can't do much. They're bad. High empowerment states are where you have a lot of controllability over the environment. You can get to many places. You can do many things. And the way we then get an assistant to help increase empowerment is by just giving it as part of the objective. That's your job, is to make sure that the person stays as much as possible in states of high empowerment. This is the example result, or one example result. Even though the assistant here cannot observe the flags and so has no idea about the goal, it nonetheless enables people to land by making sure that, basically by stabilizing the craft. And that's kind of a natural consequence of optimizing for empowerment. You get a craft that's much more stable, therefore easier to control, and you can just go ahead and land it yourself. And so I think that this alternative, right, to typical assistance, this different paradigm is I think really worthwhile thinking about. So instead of figuring out what people want and then having a really smart robot kind of do it, it seems possible to find ways to empower people to take good actions by themselves and do the task themselves. And I think that's good because ultimately they're the ones who know what they do. When we try to infer the goal, we get it wrong all the time. Um, and so if we can just enable them to do what they want, I think that's amazing. And it seems like there's a proof of concepts that we can, or else we can improve things significantly, be it by uh, getting assistance in processing information that they're getting, or making systems that adapt over time as the user changes, or by simply just optimizing for users to be empowered to do whatever they want very directly. I think all of those are ways that get at the same notion of get the person to be able to do the task by themselves, that they want by themselves. So with that, I'd like to thank you, and to also thank my collaborators on this work, especially the students who did the work, other faculty and industry collaborators, and definitely a big thank you to the UCSF Ganguly Lab, who without whom this would have never been possible. So thanks so much, everybody, and stay safe.